In exercise 20, we must calculate the minimum of the function of the cost function 2x squared plus 6xy plus 5y squared plus 2x plus y plus logarithm of y plus 50 in the set of points in R2 such that x belongs to R and y is greater or equal than 0. For it, I will start by studying the local optimums. I need the first partial derivatives, which are for x plus 6y plus 2, and the second one is 6x plus 10y plus 1 plus 1 over y. I make these expressions equal 0 to calculate the critical point, and now I solve the system. I clear, for example, x in the first equation, and I get minus 1 minus 3y divided by 2, and now I replace x in the second equation. So I have 6 times minus 1 minus 3y over 2 plus 10y plus 1 plus 1 over y equals 0. So minus 3 minus 9y plus 10y plus 1 over y is 0. So y minus 2 plus 1 over y is 0. Now I do common denominator, x squared minus 2y plus 1 is 0. So y is minus 2 plus minus 4 over 2. So y is 1. Y is 1 and x is minus 2. C is a cost function, but nobody tells us that x can't be negative. So this is a good solution, and point, I'll write in a different color, point minus 2, 1 belongs to the set where we are studying the optimums of C. So, point minus 2, 1 is a critical point of C in the set A. To know if it is a local minimum or a saddle point, we must calculate the Hessian matrix and then replace the critical point in it. These are the second partial derivatives. So here we have the Hessian matrix evaluated at any point. Then I replace the critical point in the Hessian matrix and I get this one. To study its sign, I will use the minus method because it isn't a diagonal matrix. The minors are positive and the second one is 36 minus 36, 0. So the Hessian matrix evaluated at the critical point is positive semi-definite, so we can't assure if this point is a local optimum or not by the moment. So as the Hessian matrix evaluated at the critical point was semi-definite, we need to use the concepts in Unit 1 to study if it is a global optimum or not. The first thing we must check if A is a convex set. We can see it here in the graph. It is the green zone and it is convex because of the graph. If we join 2 points in this graph, the segment connected them is included in A, and also because A is an upper semispace. Then to study if the function is convex or concave, we come back to the Hessian matrix at any point, and now we study its eigenvalues, which are, the first one is positive, and the second one is 40 minus 4 over y squared minus 36 equal 4 minus 4 over. Now to study the sign of H2, we must consider that y is greater or equal than 1. Then y squared is also greater or equal than 1. 1 divided by x squared is less or equal than 1. Now 4 divided by x squared is less or equal than 4, and finally 4 minus 4 divided by y squared is greater or equal than 0. So we have the first one is positive and the second one is greater or equal than 0. Then H evaluated at any point is positive semi-definite in A, which means that C is convex in. Then, when the function is convex in set A and we have a critical point in that set, we have that this critical point is a global minimum of C in the set A. The answer then would be that the values of f, x, y must be x equal -2 and y equal 1 to enable the firm to achieve the least possible cost, which we calculate by replacing that point in the cost function. So the minimum cost achieved would be 48 units.